Good afternoon, everyone. My name is Bo Ran, a joint doctorate student between Tsinghua University and IFSTAR. It's my pleasure to share my research idea with you. And the idea is about change of transport property caused by pore crystallization. And the presentation is sulfate diffusivity, a term by pore crystallization due to chemical sulfate attack of same-based materials. My presentation is mainly divided into 4 parts: the contact, modeling, fitting, and conclusion. My research topic is about sulfate attack on cement-based materials. The sulfate penetrates into materials, react with aluminum fins, form expensive product, here is anthracite, and lead to 3D damage. The mechanism is so simple. However, when I read the literature, I really found something special. The self-deceleration of sulfate increased, just like these two figures shows. The total sulfate amount and anthracite amount increased very slowly in the early stage, something like within 2 months during sulfate attack. That is to say, the reaction rate declined. Besides, the penetration from the two figures advanced very slowly with time. If we take a simple calculation of the results in every figure, we can say the front is not proportional to the rate of time, and the diffusion rate decreased dramatically. That is to say, we cannot consider this problem just as a simple diffusion case. Obviously, the decrease of diffusivity is induced by crystals in pores, so let's focus on what happened to pores during crystallization. Due to volume increase, the crystals replace the water to occupy pore space, but this substitution is not complete. There's a thin liquid water lying between crystal and pore wall due to surface energy. So if we still consider this thin film as a transport path, the tortuosity keeps unchanged. However, the diffusion area decreases and a constricted region appears. To simplify, we use crystal content to express the pore space occupied by liquid film and capillary water. Let's talk a little more about liquid film. In such a thin film liquid film, about 1 nanometer, 2 issues become significant: the electrical double layer and the structured water layer. The former builds a repulsion potential barrier to ion transport, and the latter enlarges the viscosity of water. These two issues will have an inhibiting effect on mass transfer. This slide gives us a quantitative demonstration of inhibiting effect. Two results are simulated based on molecular dynamics. The left shows the reduction of iron diffusivity caused by electrical double layer. The right shows the structural water layer effect. And let's take a look at 1 nanometer. It's the size of liquid film, and we can find that the electrical double layer decreased the diffusivity to 0.1 times of diffusivity in bulk water, and structured water layer has a little influence on diffusion coefficient. Summarize the characteristics of capillary and field pore in this table, including diffusivity and porosity, where theta is the reduction parameter. Then, we will derive the effective diffusivity during crystallization. As the top left figure shows, the capillary and field pore are connected in series, so we write the effective diffusivity in this form. We can say the diffusivity is inversely proportional to entry-guide amount. In addition, we can also compare and we can also consider a parallel connection between capillary and field pore. The ratio between effective and initial diffusivity is right. Just take an averaging operation. Furthermore, by using homogenization method, we express the effective diffusivity more complicated, just like the top right figure shows here. We consider the capillary pore, entry-guide crystals, and the sodium matrix as a spherical particle, and a film as a spherical shell in floating crystals. Then we can write the effective diffusivity. So now we proposed three models to express the effective diffusivity in terms of entry-guide amount, and we'll take a simple comparison among these three models, shown in the bottom left figure. In homogenization and constriction model, a small amount of entry-guide crystals can lead to a larger reduction of diffusivity. That we believe can explain the rapid deceleration of sulfate ingress in the very early stage. Next step is to validate from existing experiments. However, only apparent and equivalent diffusivity can be found in the literature. In fact, the real sulfate diffusivity is very difficult to measure because the entry-guide amount change along the diffusing direction. So we have taken indirect method before. Before that, let's review the mechanism of sulfate attack. The external sulfate penetrates into matrix reaction with annular phase to form entry-guide crystals. Just these crystals, on one hand, fill and block the pores, on the other hand, they will accumulate crystallization pressure until destroying the matrix. Besides, in natural environment, the sulfate ingress is always accompanied by the leaching, which has a great influence on crystallization reaction. So to simplify, we ignore the leaching, assume the crystallization as a first-order reaction, and we just focus on the coupling effect between diffusing and reaction. Let us translate the sulfate attack mechanism into mathematics language. First of all, the mass conservation combines diffusing and reaction, and then crystal filling in the pores is written by volume conservation. In the end, the previous three proposed models are adopted to link the diffusivity and the crystal amount. To solve the partial differential equations, we employ an explicit difference scheme. Equations are rewritten in discrete form. Then we use MATLAB to compute. By fitting two unknown parameters, reactive kinetic coefficient of crystallization reaction, and reduction parameter of liquid film, the experimental reactive entry-guide amount are simulated by the proposed diffusing reaction model. Just like this top right figure shows, the difference of entry-guide between 2 weeks and 4 weeks are very small. The fitting parameters are given in this table. The results indicate that the reactive kinetic coefficient is about 1 per square meter, and the reduction parameter in the homogenization and constriction model are close to 1, which match with the simulated results shown before. But for average model, the reduction parameters are extraordinarily small. So I have to say the obtained fitting values are only for model comparison, and if we want to simulate a real situation, the real kinetic-based data are needed. Finally, let's conclude. Firstly, all these three diffusivity change models can describe the diffusivity decrease by pore crystallization, and the constriction model gives most rapid decrease with intricate amounts. Secondly, from conceptual diffusion reaction model for chemical sulfate attack, the rapid decrease of sulfate absorption observed in experiments can be explained by the reduction of diffusivity in three proposed models, and further studies should be conducted to measure the kinetic coefficient and reduction parameter. That's all. Thanks for your attention.